Okay, so now we can continue talking about the chapter 1, structure and bonding. The next topic we are going to cover is describing chemical bonds, a valence bond theory. So now that we know that electrons occupy regions of space called as orbitals, we can have a deeper understanding of how covalent bonds are formed. So a covalent bond forms when two atoms approach each other closely so that a single occupied orbital on one atom overlaps a single occupied orbital on another atom. So that means a covalent bond is formed by the overlap of atomic orbitals. There are two common theories that are described for explaining the formation of a covalent bond. One is the valence bond theory and the other is the molecular orbital theory. So we'll talk about the valence bond theory first. So here, according to the valence bond theory, a bond is formed by simply sharing electron density between two atoms in such a way that there is a constructive interference of their atomic orbitals. So for example, here we see that this is a 1s orbital of one hydrogen atom, this is another 1s orbital of another hydrogen atom. They overlap, they both have one unpaired electrons, both in opposite spins, and they can overlap to form the hydrogen molecule. So basically the requirement for a valence bond theory is that the atomic orbitals should be singly filled, that means they should have one unpaired electron, and which are in opposite spins, and they will have a region of overlap to result in the formation of a molecule. Here is a further explanation of the same concept, that when two hydrogen atoms are placed individually on an energy scale, they are at a higher energy level than when a hydrogen molecule is formed. So when the two hydrogen atoms combine to form a hydrogen molecule, about 436 kilojoules per mole of energy is released, as a result of which the hydrogen molecule is formed. And that tells us that the hydrogen molecule is at a much more stable state than the individual hydrogen atoms. Here is a potential energy diagram depicted in this picture here, where you see that when the two hydrogen atoms are too far apart, they are at a higher energy. As they come closer, the energy keeps on decreasing, and then at a certain optimum length, they are able to form a bond where the orbitals overlap, and that is the length which is called as the bond length. The distance between the two atomic nuclei when a bond is formed is called as the bond length. So in the case of hydrogen, it is 74 picometer. Now, if you bring them any more closer, then the energy goes on increasing, because now the repulsive forces starts to act on, and so you can see that the energy is increasing. So in a nutshell, the formation of a hydrogen molecule is an energetically favorable process. And it's the same thing that's shown in this slide. Okay, now let's look at the structure of methane. Let's talk about the structure of methane based on the valence bond theory. Now methane, we all know, has the formula CH4. So CH4, right? And let's try to apply the valence bond theory to the formation of methane molecule. Now, according to the valence bond theory, remember that the orbitals should be have unpaired electrons in it. So if we write the configuration of carbon, we have carbon as 1s2, 2s2, and 2p2. Or you can write it in this manner, right, where you have them as in the energy level. So if this is the energy increasing, E, you have 1s2, 2s2, and then the p orbitals are all in the same level, and we have 2 electrons in here, right? However, if you look at the structure of methane, carbon forms 4 bonds. So here it has got only 2 unpaired electrons, which doesn't explain the formation of the 4 bonds of carbon. So we can consider this as the ground state, and excited state where the electrons from the 2s orbital are allowed to move. One of the electron from the 2s orbital jumps to this 2p orbital, and now we have 2p here, 2s, 1s. Okay, we have 4 unpaired electrons, which fulfills the criteria of the valence bond part of the valence bond theory, that there should be 4 unpaired electrons to form the 4 bonds. Okay. Now, if you think that they are overlapping with the 1s orbital of the hydrogens, then it doesn't completely explain the structure of methane, because methane has a structure where the 4 hydrogen atoms are at the 4 corners of a regular tetrahedron, and all the bond angles are 109.5 degrees. Okay, and also they have exactly the same bond length. So if you have 4 electrons which are in 2 different kinds of orbitals, that doesn't explain how they can have all the bond angles exactly the same and all the bond lengths the same. Okay? So that is where the concept of hybridization comes in. This slide here explains the structure of methane using the concept of hybridization. This was actually given by Linus Pauling in the year 1931, where he described the structure of methane by saying that the 2s orbitals and the 2p, the 3 of the 2p orbitals, can be hybridized mathematically to form a to form 4 hybrid orbitals here, which are called as sp3 hybrid orbitals. So we call it as sp3 because it involves an s and 3p orbitals to form the hybrid orbitals. This actually gives us 4, because 4 orbitals took part in the process. So there will be 4 hybrid orbitals. So these are 4 hybrid orbitals. Actually, a hybrid orbital is represented by a large lobe and a small lobe, but here the small lobes are not shown to avoid any crowding. So only the larger lobes are shown. So the larger lobes, 4 of them represent 4 sp3 hybrid orbitals. And also they all contain 1 electron each. So the shape which they would like to occupy in order to keep the minimum repulsion between the electrons is at the 4 corners of a regular tetrahedron. Now, the carbon has each of the sp3 hybrid orbital on the carbon can now overlap with 1s orbital of the hydrogen atom to form a covalent bond. So we have 4 covalent bonds, and each has an overlap of an sp3 hybrid orbital from a carbon and a s orbital from the hydrogen atom. And since they are at the 4 corners of a regular tetrahedron, all of them will have the bond angle of 109.5 degrees. And these all bonds, which are called as sigma bonds, which are formed by the overlap of sp3 hybrid orbital of carbon and an s orbital of hydrogen, as shown in this picture. Now, this is an extension of the same concept of sp3 hybridization for using the example of ethane. Ethane has the formula C2H6. Write it down here. C2H6. So there are 2 carbon atoms and 6 hydrogen atoms. Yes, as you see here again, just like in methane, we have the 2 carbon atoms, but they are both sp3 hybridized with 4 sp3 hybrid orbitals, and they can now overlap with the hydrogen atoms 1s orbital, and also they overlap with each other in a head-on manner. So they have sigma bonds. So this all result in the formation of, this is a sigma, and then here the hydrogen atoms 1s orbital. So we have one hydrogen here, another hydrogen here, another hydrogen here, right? They all overlap to form sigma bonds. These are all sigma bonds. And same thing with the other carbon atom. They also overlap with three hydrogen atoms, 1s orbital, okay, each having one electron, and that's how you can explain the structure of ethane. So ethane also has carbon atoms in the sp3 hybridized state. Now let's take another example and try to work our concept of sp3 hybridization. So here we have taken the example of ammonia. Now ammonia has the formula NH3. Now according to the valence bond theory, we should have unpaired electrons so that we can write down the configuration of nitrogen the same way as we wrote for carbon. This is 1s, 2s, 2p. Nitrogen has 7 electrons. So we have 1, 2, 3, 4, 5, 6, and 7. Okay, so we have 3 unpaired electrons, and nitrogen forms 3 bonds with hydrogen. Okay, but then we also have a lone pair of electrons in nitrogen. Okay, so the structure of nitrogen is again of a pyramidal shape. Okay, if you recall from general chemistry, and ammonia has a pyramidal shape where the 3 hydrogen atoms and the lone pair of electrons are somewhat in the corners of a tetrahedron, but the bond angles are lesser than a regular tetrahedron. It's about 107 degrees. Okay, so the bond angles are around 107 degrees. So here again, we are trying to explain the structure of ammonia using the concept of hybridization. Now, knowing that we have 3 single bonds, okay, and a lone pair of electrons, here the nitrogen again undergoes hybridization using its 2s and the 2p orbitals to give 4 sp3 hybrid orbitals. Okay, so we have 1, 2, 3, 4 orbitals taking part in the so we have 1, 2, 3, 4 orbitals taking part in the hybridization, and they result in the formation of 4 sp3 hybrid orbital. Okay, out of that, 3 of them are singly filled, and the 4th one already has a pair of electrons. Okay, this is what nitrogen's hybrid orbitals look like. And now, if you draw them out, remember we have to draw only one lobe because it's a hybrid orbital. So these are one lobes. These are single lobes of the hybrid orbital. One of them occupies a lone pair, so I'm going to draw this one out, and then these 3 are going to overlap with 3 1s orbitals of the hydrogen atom. So this is 1s of hydrogen, each having 1 unpaired electron. So we have 1 electron from the nitrogen, right? So these 1 electrons, and then hydrogen also has 1 electron, and that's how ammonia is formed. So again, the hybridization of nitrogen atom is sp3. Here we have the lone pair of electrons. The bond angle here is lesser than a regular tetrahedron because of the repulsion between lone pairs and bonding pairs. So we can write down the bond angles of close to 107 degrees. Okay, so I would like you to do as practice. So practice drawing a water molecule using the concept of sp3 hybridization. Okay, that means oxygen will be sp3 hybridized, and then it will form sigma bonds with hydrogen atoms, and then there will be orbitals which will have the lone pair of electrons. So first of all, you should draw out the structure of water and then predict the geometry, predict the hybridization, which should be sp3, and then draw this out in this manner. Okay. Now let's consider the structure of a compound bearing a double bond. Example is ethylene. Formula is C2H4. C2H4, and it has a planar structure with a double bond between the 2 carbon atoms. Okay, so we have a double bond between the 2 carbon atoms, and then hydrogens at an angle of 120 degrees. The hydrogen-carbon-hydrogen angle is 120 degrees. Okay. Now ethylene, since it exhibits a planar geometry, So we can explain the structure of this satisfactorily by hybridizing an s and a p s orbitals and the p orbitals again. However, unlike in case of methane, here we need only one s and two of the p orbitals, and one of the p orbitals actually is left unhybridized. Okay, so this is the ground state configuration of carbon. This is the excited state. We have 4 unpaired electrons. So this is my 1s, 2s, and 2p. Electrons from the 2s orbital and 2 of the 2p orbitals take part in hybridization to give this sp2 hybrid orbitals. And how many hybrid orbitals do we get? We get 3, and this is for each carbon atom. Now remember, the ethylene has 2 carbon atoms, so this hybridization happens in each of the carbon atom in exactly this same manner. Okay, so if you draw the pictorial representation of the orbitals, you can see that the green lobes here, this is one of the carbon atoms, and this will be exactly the same for the other carbon atom. The green lobes represents the sp2 hybrid orbital. Each of this sp2 hybrid orbital has 1 electron each, and then we have the 2p orbital, which has the one unpaired electron, but it is in the unhybridized orbital. Hence, this p orbital is shown with a blue and a red lobe, telling us that it is the unhybridized orbital. Okay, so now if you look at, so in this slide you can see that the two carbon atoms, each with sp2 hybrid orbitals and one unhybridized p orbital shown. The green lobes represent the sp2 hybrid orbital with 1 electron each, and then the unhybridized p orbital has also 1 electron. Each carbon atom in the ethylene, they form sigma bonds by the overlap of these sp2 hybrid orbital. So this green overlap region represents a sigma bond, and these green sp2 hybrid orbitals are free to overlap with the s orbital of hydrogens. Okay, so if I go ahead and draw this in the form of hybrid orbital, so we have 2 carbon atoms. Okay, we have one sp2, a second sp2, and a third sp2. The same thing with this carbon atom, right? This has a sp2, sp2, and an sp2. Then these overlap with hydrogen atoms to form sigma bonds, and these overlap with each other to form another sigma bond. Okay, so we have sigma, 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 and sigma. Okay, so if you look at, let me draw this carbon as green. So this is a carbon atom, this is a carbon atom. Okay, and we have the unhybridized p orbital sitting here on each of the carbon atom, and they also have 1 electron. So we need to overlap these also in order to complete the octet of so we need to overlap the p orbitals also in order to complete the octet. So they cannot do head-on overlap to form a sigma bond anymore because they are present perpendicular to the plane. So the only way they can overlap is by lateral overlap. So they come closer and they form a lateral overlap, which is now called as a pi bond. Now remember that even though it is shown an overlap here and an overlap here, it doesn't mean you have 2 pi bonds. There's only 1 pi bond. It's just that the top lobe and the bottom lobe are overlapping. So in this structure of ethylene, we have carbon with a double bond to the other carbon, single bond to the hydrogens. Each of the single bond represents a sigma bond, and in the double bond, one of them is a sigma and the other one is a pi. Okay, remember sigma bonds are formed by head-on overlap and pi bonds are formed by a lateral overlap. We also have this as sigma, 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 and sigma. So I hope you have understood the sp2 hybridization in case of ethylene. We'll talk about sp hybridization in the next slide. Let's consider the bonding structure of a compound with a triple bond, and an example of this is acetylene. Here the 2 carbon atoms have a triple bond, and then there is single bond between the carbon and the hydrogen atoms. A triple bond is formed by sp hybridization, where one of the s orbital and one of the p orbitals take part in the hybridization, resulting in the formation of two sp hybrid orbitals, and the two p orbitals with one electron each, we show them as the unhybridized p orbital. So if you look at the picture here, orbital picture, we have the green lobes again represented as the hybrid orbitals. Now it is sp, and we have two of them, and this will be for each carbon atom. Remember, we have two carbon atoms, so this is the hybridization shown for one of the carbon atoms, and this will be the exact picture for the other carbon atom. And now we have these p orbitals which did not take part in hybridization. They are the unhybridized p orbital sitting perpendicular to each other. Okay, so if you look at the next slide, these are the two carbon atoms. The green lobes represents the sp hybrid orbital with one electron each. The red lobes represent the unhybridized p orbital. Okay, so once the two sp hybrid orbitals overlap to form a sigma bond, the p orbitals will overlap sideways in this manner to form the pi bond. Okay, so in our structure of acetylene, which has got C triple bond carbon with a hydrogen and a hydrogen. Okay, so here we have this as a sigma. One of them is a sigma, which is this one, the green lobes overlapping. This is also a sigma, but then we have these two bonds as the pi bonds, which are formed from the lateral overlap of the p orbitals, unhybridized p orbitals. This results in the formation of a linear structure with a bond angle of 180 degrees. Now that we have learned about the different kinds of hybridization, this chart here compares the bond length and the bond strengths of the different hybridization involved with carbon atoms. So you can see here that when you have two carbon atoms which are sp3 hybridized, the bond length is around 377 kilojoules per mole. When it is two carbon atoms sp2 hybridized, the bond strength has increased to 728, and between sp hybridized carbon atoms, the bond strength has increased to 965. Right? So in a summary, we can say that as the multiplicity of the bond increases, the bond strength also increases. Now let's compare the lengths of the bond. So you can see a carbon-carbon single bond is 154, carbon-carbon double bond is 134, and a carbon-carbon triple bond is 120, which tells us that as the longest bond is for that of a single bond, then comes the double bond and then the triple bond. So as the multiplicity of the bond increases, the length of the bond decreases. This is a simple way of figuring out what will be the hybridization of an atom. You just have to count the electron clouds around the central atom or the atom which is in question in order to figure out the geometry and the hybridization. So if you have two electron clouds, then the bond hybridization is going to be sp, bond angle is 180. The geometry would be linear. If there are three electron clouds, it would be trigonal planar with a bond angle of 120 and sp2 hybridization. And if you have four electron clouds, then the geometry is going to be tetrahedral, bond angle 109.5, and hybridization is sp3. So let me quickly show you an example here for each one of these. So for example, if you have a compound like this one, say if I draw HC triple bond N, okay, if I draw the Lewis structure of HCN and ask you to figure out what is the hybridization of carbon atom here. So you can count the electron clouds. So this is an electron cloud. Let me use a red, this is one electron cloud, and this whole thing is considered as one electron cloud. So two electron clouds means the structure is going to be linear with a sp hybridization. So the hybridization of carbon atom here is sp. Now if I draw another structure with a carbon here with double bond to oxygen, and we have say hydrogens here, okay, and then ask you to figure out the hybridization of carbon atom here, again we are going to look at the electron clouds. So we have one electron cloud, two electron, and the third electron cloud. So the 3 electron clouds means it has to be sp2. Okay, so if I use this yellow here, so this is 1 electron cloud, this is a second, and this is a third electron cloud. So that means we have a sp2 or 120-degree bond angle with a terminal planar geometry. Okay, so you have to count the electron clouds around the central atom to figure out the hybridization. For as an example, for the third one with the tetrahedral geometry, say for example I draw out water molecule, right? HOH. Okay, so this is my water molecule. Now, how many electron clouds do you see? You can count this as 1 electron cloud. Lone pairs are considered as another electron cloud. So we have 2 lone pairs, so 2 electron clouds. Third one here and the fourth one here. So 4 electron clouds. Geometry will be tetrahedral on angle 109.5. This is in for a perfect tetrahedron. Okay, it's not the case in water because we have lone pairs here, but the hybridization of the oxygen atom here would be sp3. Okay, so this is very easy to figure out the hybridization if you know how many electron clouds are present in your central atom or the atom in question. Let's do a question here to check your learning. Question is asking you indicate the hybridization of the orbitals on each carbon 1, 2, and 3. Okay, so we are looking at a carbon atom which has got 4 single bonds, and 2 of the carbon atoms have triple bonds, right? So when going back with our easy way of figuring out the hybridization, if the carbon atom has 4 electron clouds, so this is 1, 2, the carbon atom here has 4 electron clouds, 1, 2, 3, 4. So 4 electron clouds means it has to be sp3. And let's look at the next one. The carbon number 2, it has got 2 electron clouds. Remember, triple bond here is considered as 1 electron cloud. This is another, so 2 electron clouds. So it will be sp. And then what about the third one? Same thing, it has got 2 electron clouds. Here is 1, here is 1. So that will be sp again. Okay, you can go ahead and check your answer. But it's explained here, and so we have the sp3, sp, and sp hybridization. Okay. One more question. Consider the structure of urea. What is the hybridization of the central carbon atom? This is the central carbon atom. So you can again count the electron clouds. This is 1, 2, 3. So remember that 3 electron clouds, right? 3 electron clouds means it has to be sp2. Okay, sp2 hybridization. So carbon atom here is sp2 hybridized. So here is the key to the previous question, that how many electron clouds are there in the carbon atom in urea? It has got 3 electron clouds, and the hybridization is sp2. In the next slide, I have posted a YouTube video which summarizes the concept of hybridization. You may want to watch that not in the presentation mode, but in the normal mode, because then only you'll be able to see the complete video. Okay. After you watch the video, I would like you to be able to answer questions from the worksheet and also answer questions from the end of the chapter problems regarding hybridization concept. So here is